Hey there, and welcome to The Explainer. What do you think a perfectly thrown football has in common with a planet orbiting the sun? It feels like nothing, right? Well, it turns out the answer is a whole lot. Today, we're going to get into the physics that governs pretty much everything that moves.
It sounds impossible, doesn't it? A quick toss, a cosmic dance that lasts for ages, a tiny ticking clock. They couldn't be more different. And yet there's this hidden connection, a secret set of rules that's running the show behind the scenes for all of them. And that is the secret. Physics, it isn't just some boring subject you had to take. Think of it like a language that describes the universe. And once you learn a few words, you can start to read the story of how everything works. So, today, we're going to learn to speak it.
All right, so where do we even begin? Well, just like learning any new language, you gotta start with the basic vocabulary, the keywords that form the building blocks for everything else.
And what's so cool about this language is how simple it is at its core. You don't need to memorize a giant dictionary. Nope, you just need to get a handle on a few key words. Stuff like force, a push or a pull. Velocity, that's just speed with a direction. And acceleration, which is any change in that velocity. That's it. You get those three down and you're already on your way.
Okay, so let's try to put our first sentence together. We're going to do that by looking at something we've all seen a million times. That perfect, graceful arc of something being thrown. Physicists have a name for this, of course. They call it projectile motion. So the big secret to understanding this beautiful curve is that it's actually two really simple things happening at the exact same time. First, you've got the vertical motion. The object is just falling, pulled down by gravity. Early physicists called this modo di caduta libera, or free fall. Simple enough. But at the same time, it's also moving horizontally at a constant speed, just cruising along. You put those two simple motions together, and voila, you get that perfect arc.
And this is where it gets really powerful. Because once you separate those two motions, you can basically predict the future. Seriously. You can calculate the exact horizontal distance that thing is going to travel. That's its range, or as it's known, its gittata. It's almost like having a cheat code for reality.
And this is the real beauty of it all. That whole flight path, the going up, the peak, the coming down, it can all be wrapped up in one single elegant rule. It's called the equation of the trajectory, or equazione della traiettoria. It's the entire story of that arc, told in one perfect little sentence of math.
Okay, so we've got arcs down. Let's move on from lines and curves to circles. It's time to talk about the physics of things that spin. I want you to picture this. You're on a merry-go-round, right? And you feel that force that's just trying to throw you right off the side. You've got to hang on for dear life to fight it. So what is that? What's that force pushing you out?
Okay, get ready for a bit of a mind bender. That outward force you're feeling, it's not real. I know. Physics tells us that the only real force in this situation is actually pulling you in. See, to make anything move in a circle, you need a force that's constantly pulling it toward the center. That's called the centripetal force, or forza centripeta. Think about the tension in a yo-yo string, or, the grip of your hands on that merry-go-round. That's the real force.
So, what in the world is that feeling of being flung outwards then? It's just inertia. That's it. Your body wants to go in a straight line. That's what objects do. But the ride is constantly yanking you inward, forcing you into a curve. That force you feel is just your body's own momentum fighting against that real inward pull. Now, to get really precise about describing this spin, we have a few special terms. There's a spostamento angolare, which is just a fancy way of saying how much it's rotated. Then you've got velocità angolare. That's how fast it's spinning. And finally, accelerazione centripeta, which measures that all-important inward acceleration that makes the whole circular thing happen. All right, so we've covered arcs and we've covered circles. The last phrase we're going to learn in our language of motion is all about rhythm. That steady back and forth swing. Physicists call this harmonic motion.
So let's look at two different systems here. You've got a mass bobbing on a spring, and you've got a pendulum swinging back and forth. They look pretty different, but they share the exact same secret. In both cases, there's what's called a restoring force, or a forza di richiamo. that's always trying to pull the object back to the middle. For the spring, well, it's the spring itself doing the pulling. For the pendulum, it's gravity. And this restoring force, it's the engine behind all rhythmic motion.
And this whole idea leads to something totally wild about pendulums. It's a principle called isochronism. And what it means is that the time it takes for a pendulum to make one full swing, its period, has nothing to do with how heavy it is or even how wide you swing it. Nope. The only thing that changes the timing is its length. That's it. It's so reliable and so counterintuitive. And it's exactly why pendulums were the key to making accurate clocks for hundreds of years.
Okay, so we've learned these three different phrases in the language of motion, right? The arc, the spin, and the rhythm. Now it's time to bring it all together. Let's talk about the master key, the one big idea that connects all of this. Think about it. The arc of a ball, the spin of a merry-go-round, the rhythm of a pendulum. They seem so different on the surface, but we've seen that they're all just different stories told with the same words, force and acceleration. It's all the same language, just describing different things.
So what's the glue that holds all these concepts, position, velocity, acceleration, together? Well, physicists have this incredibly powerful tool from calculus. It's called the derivative, or derivata. Now, you don't have to do the math here, just get the concept. Think of it like a special lens that lets you see the rate of change at one single frozen moment in time. It's the verb of our language. It's how we can precisely get velocity from position and then get acceleration from velocity. It is the deep underlying grammar that makes the whole language of motion work.
And that is the real power of physics. It's this incredible language that uses the same exact rules to describe the flight of a ball, the orbit of a planet, and the ticking of a clock. So I'll leave you with this question to chew on. If this relatively simple language can help us decode the unbelievably complex dance of the cosmos, what other complicated systems in our world are just waiting for us to figure out the right words to understand them?